So I know section 10.1 took some time. It was nearly a 30-minute video. This section isn't going to be as long. There's not as a lot of introductory terms to go over. What we looked at in section 10.1 was the process of collecting the data. For the example of the car rental agencies, we had to calculate all of the columns of information, find all the sums. We talked about when constructing a scatter plot, all we have to do is really just plot our points, compare or create ordered pairs from our x and y values, and we can just make a sketch of a scatter plot that's very easy to do, just to regenerate one in today's examples as well. We looked at the formula on how to calculate R, just filling in all the values and then typing that formula with the values in there into our calculator. Today I'm going to show you from a list and spreadsheet how R shows up when we run the stat calculations. And then we went through the process of testing the significance of a relationship. What we're going to do in section 10.2 is determine the equation of the regression line. So as we're looking at our scatter plot, we're going to draw in a line of best fit. First just by hand, and then we'll have the calculator do that as well, and then it will generate an equation for us. But there's also formulas to follow, just in case you don't have the Inspire that you're working with right now. You could still use these formulas to get the different values for the slope and the y-intercept. So we call this regression analysis. All right, so this is just a general, generic scatter plot that I created. These points don't really come from any data that we looked at in the past, but go ahead and just make a quick sketch of this. Again, we looked at our independent variables, so this was our x-axis and our y-axis. And then even though we have some points, and this is where outliers can also affect our line of best fit that we're going to draw in. If we were to remove a point, which I'm going to mention at the very end, how will that affect our line of best fit? So that's something that we can explore in the future as well. So if you tend to notice, for the most part, these points do seem to look like we've got a positive correlation, a slight positive correlation here, that as x increases, y is increasing. We might have some points that just don't follow this behavior, but there's not too many of those. So once you have the sketch, hopefully with a ruler or some sort of straight edge, we do want to draw in a line of best fit. So maybe when we go to sketch this, we just want our points to sort of be centered around it. Ideally, we would love it if our points were to just line up themselves, that we could draw a line that would go through all of them. But if not, we might have something that tends to look like this. And if we had to do this even more so by hand, which back in the day this is how stats was calculated here. So we have a regression line, which is also known as the line of best fit. We tend to call the process here as the least squares regression. And in looking at this, we sort of want to find the distances that each point is from our actual line here. So what I would say, if this is point 1, I would just call this distance 1. Here we have a second distance. We have a third distance. It's rather short. We have our fourth distance here. Distance 5 is really short, really small here. We have another distance here. We'll call it D6, our 7th distance. And then we have an 8th as well. So we have 8 points plotted here. And we're just looking at the distances, how far away the points are from the actual line. Points on the line, any point that we could sort of say will be on the line, is also known as a predicted value. Once we come up with the equation for this line of best fit, that's where we can make all of our predictions. So the points that aren't on the line, those are our actual data values. Those are our observed values. So I'll just say all the blue points. Those are the observed values. And we're just trying to see how close to the predicted values here are the observed values. So again, we're always looking for the smallest one. So we say this is the least squares regression. We don't really go into this, but I like for you guys to hear the wording that I'm going to go over. It's the sum of the squares of the vertical distances from each observed value to the line. We want that to be a minimum. So that's how we're kind of coming up with our line of best fit. But the least squares regression line is how it's also referred to. The purpose of drawing in the line of best fit or the regression line is to see a trend and to be able to make predictions, again, on the basis of the data. And we always try to calculate R first. If we see that there is not a significant correlation, there's no need to determine a regression or try to figure out a regression line when R is not significant. There's no regression, or any regression we would come up with, it would just be meaningless if there's no relationship between the variables. So just to go back over what the information we looked at from section 10.1, when R is closer to a +1 or -1, then it's substantial. The observed values will lie closer to the line of best fit, as we saw in those 6 examples of the scatter plots when R was changing, or the different values. When R is equal to ±1, all the points, the data points, will fall on the regression line. So notice the difference when R is just getting closer, or when R is exactly equal to ±1. Again, if R tends to be between -0.5 and 0.5, very close to 0, or in between 0 to 0.5 and 0 to -0.5, we would say there's not a significant difference between R and 0, so we could say that it's not a significant correlation, or that one exists. All right, so to determine the regression line, we're switching a little bit. We are going to see slope-intercept form as we've always known it, y = mx plus b. And it's really the same thing here. They're just using 2 different variables. And I know there's a b here, so please don't get it confused with the y-intercept. In this case, we're going to use that. And this is just indicating, it's for my calculus students, that is not a derivative. That's just saying like y prime. That's just the notation they use. It's still just y is equal to a plus bx, where in this case, using this notation, a is the y-intercept and b is the slope of the regression line. We're going to round both of these values to 3 decimal places as well. So please make sure you copy this down. Here's the formula. So if you don't have an Inspire calculator, here's the formula that you just have to calculate. Notice, like in the car rental example, we found all of these values, but the calculator, even on Google Sheets, it could run the sum for you to calculate these. But I'm not going to give you too much data at once to be too overwhelming. But notice we have the sum of y's, we have the sum of x squares, we have the sum of x times y. So we found all of these in our columns anyway. So it's very similar to the formula to find R, but I think a little bit less or simpler than doing so. Here B, notice again we still have some of these totals are just arranged in a slightly different order. So please copy these down. We're going to go back to the car rental example that we did in section 10.1. We're going to calculate both A and B. So I just rewrote the values. Again, we're going to round to 3 decimal places for both A and B. So in that example one, the car rental companies, we already found R. So keeping in mind, we said we found R to be a 0.982, which told us that there was definitely a correlation between the 2 variables, a very significant relationship there. So this tells us we can proceed to find the regression line. So from the data, n was equal to 6. Sum of x was that 153.8. Sum of all the y values was 18.7. All the x values squared, the sum of those was 5859.26, and then the sum of the product of x times y was 682.77. So we're going to go ahead and go back to finding A. And if you look at what you wrote down, this is where all the values are going to fall, and we're going to calculate this. So pause the video, see what you're coming up with. All right, so you should be getting a 0.396 for A. We're going to calculate B. These are all the values we need to substitute in here. Go ahead and pause the video and calculate this. Again, round to 3 decimal places, we should be getting a 0.106. So right now, we could say that our regression line equation in the form of y equals a plus bx is going to be y equals the a is the 0.396, still put that little apostrophe there, plus 0.106x. So this is our equation of our line of best fit, and we're going to be able to make predictions later on for any given x value. We can know the output of this. So this is what we're after in this section, is the regression line. All right, so some things to know. The sign of R should still be the same as the sign of the slope of the regression line, because if we have a negative correlation, we're going to have a line of best fit that's going to have a negative slope. If we have a positive correlation, our line of best fit should be going uphill from left to right. Therefore, that slope should be a positive slope. So that just ties in nicely. It wouldn't make sense if they were completely different. All right, some other things to know. The regression line will always pass through the point whose x-coordinate is the mean of the x values, because it's the one right in the middle, and that's where we want our line of best fit to show up, and whose y-coordinate is the mean of the y value. So it's the average of all the points, which makes sense because we want it to be centered, or right in the middle. All right, so in this next example, we're going to use the equation we just came up with. I have it rewritten here to predict the income of a car rental agency that has 200,000 automobiles. So remember, this is the X value, and if you go back to the columns that you guys have in your notes from section 10.1, this was given in the 10,000s. So that means in this case, X is really equal to 20. We don't want to put in the whole 200,000. So if we divided 200,000 by 10,000, that leaves us with 20. So we want to just go ahead and substitute this in. 0.396 plus 0.106 times 20. So we're predicting the revenue when there's exactly 200,000 cars on the lot. Going through this, go ahead and run the calculation. Turns out to be 2.516, but remember this is in the billions of dollars. All right, so what we could kind of conclude from this is when the rental agency has 200,000 cars on the lot, the revenue will be approximately $2.516 billion. And that's how we can use everything that we've done since section 10.1 into 10.2 now, the connection between these two sections. All right, so how to check on a calculator. If you do have your Inspire, you can follow this. If not, still follow along. And this was pretty nice. If you guys do go to TI Inspire website and look for these two symbols for a download, you can't do this on your Chromebooks, but if you have your own Surface Pro laptop, tablet at home, you can get both of these. It's the TI Inspire CX. So you're looking for the one that has the red and the blue circles, which is a very nice feature if you don't have your own graphing calculator. But just to show this, we're going to go to add lists and spreadsheets, and I'm just going to add the data from, let me reconnect my keyboard to this, but from the car rental agency problems. So right up here, let's get this going. All right, so we want to type in an X, and then the values we're typing in, we started with 63. Go back to the data here. All right, so we had 63, 29, 20.8, 19.1, 13.4, and 8.5. But now a difference is we're going to go in column B, we're going to type a Y here, enter those values for the revenue. We have 7, 3.9, 2.1, 2.8, 1.4, and 1.5. So we're going to run the stat calculations. Remember, we need to be in a cell that doesn't have any data in it. And I'm going to go to menu. We're just going to go to for stat calculations. But now we're dealing with two variables. And then I'm also going to show you this too, but I'm going to show it to you in a separate, we're going to go to the another page to do that. So we're going to go, oh, I didn't want that. Go back to menu, stats. We want the two variables. Why does it keep going? Start one more time. Right, stats, stat calculations, and I want the two variable statistics. Oh, okay. So what we want to change here is instead of seeing this B, we want to see it's the apostrophe X, and then the next one we want to choose the Y. Everything else should be good as long as this says C, we should be okay. And then we see some data. I'm just going to scroll a little bit over to the right. And I want you to take a look at these values here. Notice some of these numbers. Look at the sum of x squared. That was one of the calculations we had to come up with, the 153.8. There's the sum of the x. So this is what's nice. It can calculate this for us. I still want you to use the formulas, but this is just a nice way to check. Notice it says n is equal to 6. We don't really need the y bar. Here's the sum of y's at 18.7. Sum of y squared is 80.67. And then what I want you guys to see, we see the sum of x times y. But here's r. Remember we came up with r is 0.982, so it shows us what r is. It also shows us the min quartiles here, which we don't need for this information. But there's a way to check everything using the stat calculations. Next, I'm going to go to a new page. I want to go to the add data and statistics. We're going to come up with a regression line here. So here's what my scatter plot would look like. So if I asked you guys to plot these points, this is what it tends to look like here. And then I'm going to click to add a variable. I want X. And then I want Y. Actually, this is the scatter plot. The first one just had the points all over the place. But once we define the X and Y axis, because if you remember, our slope was positive. So we have our points going upward in a general direction. We've got this point all the way over to the left here. But we're going to go ahead and have the calculator draw in the line of best fit. So we're going to go to Menu. We want to analyze this. So now if you go to Regression, so it's Menu 4.6. Now, even though they do have the MX plus B, we're using the A plus BX. So as soon as you click on that, even though we rounded to 3 decimal places, here's that A at 0.396, and then here's B at 0.106, but this matches our equation. So it's Y equals 0.396 plus 0.106x. We're rounding, so we're getting that approximate value. All right, so the rest of the notes here are just some things to keep in mind, but please copy them down. I'll just read over each one. The prediction value obtained is called, so that that 2.516, I think it was on the last page, that prediction value is called a point prediction. There's no degree of accuracy or confidence that can be determined. We do talk about, or there exists something called a marginal change, and it's just the magnitude of change. If we were to simplify everything to just one unit, it's the magnitude of change in one variable when the other changes exactly 1 unit. So looking at our example, if our slope is 0.106, this translates into, for an increase, because remember x was given in tens of thousands, so if we just increase by 1 unit, meaning another 10,000 cars, the value of y changes, just change in y over change in x, approximately 106 million on average. So for an increase in 10,000 cars, for every 10,000 cars we get, the value of y will change $106 million on average. When r is not significantly different from 0, the best predictor of y is just going to be the mean of the data values of y. And extrapolation is an outside prediction. When we do talk about like an interpolation, it means our x value could be somewhere within our domain of x values, but an extrapolation is like an outside prediction beyond the bounds of the data. So based on present conditions and on the premise that present trends will continue, but they need to still make sense. So predictions must be interpreted very carefully here. So here's an example of where we have to use common sense to really discuss this. Based on current consumption and known oil reserves at the time in 1979, experts said the U.S. will run out of oil by the year 2003. The price of gallon of gas was predicted to reach $10 just a few years later. So we really have to be careful with what our data is saying and with the situations it's pertaining to. We have influential points, this is what I was talking about earlier. If we feel we have an outlier, if we test the data for outliers, they can definitely affect the equation. And what they do is they always pull, we saw this with like means and medians, they pull the data towards themselves. So if we were to look at data and we did have an outlier and we did the regression line, we figured out the equation for the regression line with the outlier in there. If we remove the outlier, the graph line with point, test for an influential point, we were going to graph the line with the point, then without the point, and see if the second line changed considerably, just to see how much that outlier affected our line of regression. All right, so like I said, this section was a lot shorter, but I wanted to show you guys how to use the calculator with all of this. So unfortunately, when I go to make this a PDF, I could put the pictures in of the calculators, but very good if you've already watched this video to really see the step-by-step calculations on the calculator. As always, guys, I'll give you worksheet 10.2 along with this, solutions by the end of the week. Let me know if you have any questions.